between chaos and ergodicity. And so this will be a little bit of a riff on the same sort of theme, but very different. So okay, yeah. So I'm going to talk about mixing, so ergodicity, but in the context of Markov chains. And I will try to make a link to quantum mechanics and sort of ergodicity in the way we usually think about it in terms of eigenstate thermalization hypothesis and random matrix theory, and try to kind of link those two topics. And I thought that was like a good idea for this conference given the title. But I have to announce that basically because of that, it's the first time I've ever give kind of a talk about it. So the talk might be very shitty. So, because I don't know how people will respond, you know. So it's like I don't know, is it all trivial? Am I gonna go way too fast? So we'll find out. And so the work is done in collab. Most of it, I will describe some other work too, but most of it is in collaboration with one of my students, Aleph Orfi, and she did most of the work when she was still an intern in my group, basically. But okay, so I want to talk about mixing of Markov chains. And so why? Well, what is this? Oh, I should maybe press this thing first because of the. So this will be also tying back to some other things that we heard from Nikita and company on we are building these big devices, you know, quantum computers, and we would like to do something with these quantum computers that is maybe very hard to do for classical computers. And so a lot of us are thinking about, wow, how do we come up with good problems to do on quantum computers? And a whole set of different proposals, and these are sort of listing a number of, let's say, seminal papers on that, have to do with sampling, you know. With sampling, and I think Nikita described it very well in the colloquium yesterday, so I don't really need to like drag this on for too much, but it's basically because sampling is a very natural thing to do for a quantum device because of Born rule, right? I mean, I take a quantum system, I measure the quantum system, I will get with some probability certain states out, right? So it's quite natural for a quantum device to be able to generate complicated samples. And then the question is, can we control these devices well enough so that we can get samples out of distributions that we can say something about that are, for example, hard for a classical computer to sample from? And okay, we know a bunch of these examples like random circuit sampling or boson sampling. And so this is like some route towards, let's say, quantum advantage. But the downside of those kind of proposals is a bit like, yeah, well, I mean, boson sampling isn't useful for anything, right? I mean, and neither is random circuit sampling. Okay, you can maybe come up with some very niche application of random circuit sampling, but to a great degree, it's not extremely useful. So it would be nice if we could sample from something useful, right? And so it would be nice if we could sample, well, from a Gibbs distribution, right? So imagine that I have a Gibbs distribution of a classical Hamiltonian, and here X you should think of as some bit string, and I have some probability distribution over these bit strings given by some Hamiltonian. And well, now you see why I'm talking about it, because the conference is about thermalization. So how much more thermal can I be than basically in a thermal state? Well, depending on what the classical Hamiltonian is, yes.
It's like the long-range overall kind of stuff.
Exactly. So for example, if this would be containing, I could encode, I will give you some examples in a second, but I could encode, for example, here some JIJs between bits, between spins, you know, that basically would put a constraint that they live on a graph and I cannot have two ups that are neighbors. That defines independent sets. And for example, sampling uniformly independent sets from even relatively easy graphs is actually a Sharpie hard problem. So it's not so hard to, I mean, think in physics terms, think about a spin glass Hamiltonian, you know, like random tree set or some other type of thing. So then under some assumptions, this is classically extremely hard to do. And then we want to ask, can we do this quantum mechanically? And one idea, and I don't know how fast I can go through it. We came up with one idea, which I think is kind of nice, and I just want to show it a couple of years ago. Okay, let me first say, how would you classically do it? Okay, classically, we might want to sample from this by doing some classical Markov chain Monte Carlo, right? So I take some configuration Y of some spins, and I'm gonna, in the first step, what am I gonna do? I'm gonna propose some new bit string X conditioned on Y. I mean, this is just a way to say, in this case, I'm gonna flip the spin over here, down. This is like single spin flip proposal, but in general, this could be some distribution, like some conditional probability Q X given Y. And then I'm gonna accept this proposal or reject this proposal based on some Metropolis Hastings or Glauber type rule that gives me detailed balance, and thereby I will converge to the Gibbs state, right? This is the standard way we do it, or that's one way to do it. And basically that means this defines some kind of Markov process. I'm going to call it P. And this Markov process will have a stationary state. And if the chain is irreducible and all of that stuff, then I'm guaranteed that the stationary state of this procedure is the Gibbs distribution. And that means since it's stationary, it doesn't change when I apply P. So it has eigenvalue 1, of this matrix P. And that means that how long is it going to take to evolve into that stationary state? Well, that's just set by the second largest eigenvalue, right? And that second largest eigenvalue we call the gap delta. So it's 1 minus the maximum of the eigenvalues lambda, excluding 1. And this tells us how long it's going to take, And okay, more formally, the mixing time, so the time it takes to equilibrate to the stationary state, you see it's basically lower and upper bounded by the inverse of this gap. And there are just some factors of like, you see, if I want to get epsilon close to the final stationary distribution, yeah, you can expect that there are some logs of epsilon, because you can't really reach the state. You can just get close, And of course, if you don't have overlap, if you're orthogonal to the final state, well, yeah, then you're also not going to reach it, right? So there's some you need to have some minimal overlap with the final distribution. But you see that the scaling is just 1 over the gap. And a good Markov chain is one in which this gap, therefore, is as big as possible, right? And so what's the problem? Well, in many of these glassy problems, this gap becomes exponentially small. And so I will need to wait exponentially long to reach this stationary state. And so that's the statement in which we usually talk about ergodicity in terms of this Markov matrix, right? Okay, so now I want to somehow make this quantum, right? And I'm going to propose to you 2 ways to make this quantum. And the first way is to replace, and so this we proposed, you see, in 21, a while ago. The first is to really try to use this thing that I said earlier, that is that, if I have a Born rule gives me samples. So if I could prepare somehow the square root of this distribution, so I prepare an equal superposition of all these classical bit strings, but weighted by the square root of the probability, then obviously if I measure them in the computational basis, I get each bit string with the correct probability, right? And so you could call this the Gibbs state. So this would be a one shot. In classical terms, you would call this a Gibbs sampler, right? There's no repetitive process. There's just a state preparation process. Prepare this quantum state and measure it, right? So, well, how do we prepare this quantum state? It's like, oh, nice, but what about preparing this state? So, okay, this may be a lot to go through, but there's something like this you could do. Okay. There is a classical Markov chain along the lines that I just presented. Think about single spin flip Metropolis Hastings. This defines a classical Markov chain. And now, I mean, many of you might know, but in case you don't know, if you have a detailed balanced Markov chain, there always exists a similarity transform that makes this Markov matrix symmetric, right? And so, well, how do you do that? Well, just essentially multiply on the left and the right of this matrix by the square root of the probability and the inverse of this probability. But now if it's a symmetric matrix, well, I might as well just call it the Hamiltonian, right? because it's a valid Hamiltonian. And so, of course, now you see the stationary state of this Markov chain is eigenvalue 1. So it's the largest eigenvalue. So if I want to phrase it as a Hamiltonian of which I might want to find the ground state, I can do 1 minus, you see this similarity transformed Markov matrix. That means that the ground state of this matrix is now the thing that I'm looking for, right? That's my stationary state. And okay, if I want to make this extensive, yeah, then I can just multiply by n. That's it, right? This is, I still didn't do anything, but this is now you can call this a parent Hamiltonian or some Hamiltonian who you know has the same spectrum because this is a similarity transform, so it has the same spectrum of this Markov matrix, and its ground state is the thing that you're looking for. So if you could prepare this ground state and measure it, then you're done, right? So obviously, like this, I can't immediately get any speed up at all because I just told you that the spectrum is identical, right? So I'm not going to be able to maybe do this faster quantum mechanically than I can do it classically because the spectrum didn't change. And so here is the sort of trick. I'm just going to show some examples. If you want to know the sort of more details, you can just look at the paper. But I think it's insightful to just show some examples. So let's do this for the 1D Ising chain. And I'm going to just do single spin flip Metropolis Hastings. And if you trust me, the Hamiltonian that comes out looks like this. So I do single spin flip Metropolis Hastings to sample from this classical Ising chain. So what does this, yeah. Because the energy only depends on the neighbors. So I know how to accept and reject based only on my neighborhood, right?
That similarity transformation.
Yeah, it stays local, right? Because the similarity transform is basically with a classical Hamiltonian, so it doesn't propagate. There's no, you see, because the similarity transform here is classical, so all the terms commute in there. They're only sigma.
Okay. It's because of that, because there are only sigma z. So that's actually a product of local.
Exactly. So
It's
this is
a product
fully
of local
commuting,
terms.
and so as long as m was local, the whole thing is local.
Yeah, that's okay. Thanks.
The 1D Ising model, classical Ising model. So it's just a 1D Ising chain. And so what you get back, you see, is like, oh, again, the 1D Ising chain, right? Z on neighbors with some coefficient. This coefficient depends on temperature, right? Because you see that after I do this similarity transform, yeah, all the parameters are sort of beta dependent, right? So I get some coefficient J, which is some caution, tanh, whatever, some things that depend on beta. I get a transverse field. That's not so surprising, right? Because I'm doing like single spin flips. So basically in this Hamiltonian, there has to be some sigma x. And I mean, Anto just asked this question. It's like, but you know that you need to accept and reject based on the energy, which is determined by your neighbors. So that means that there has to be some conditional flip, right? Which is that I flip, well, somewhat like dependent on the z's of the neighbors, right? And okay, this is...
Which terms come from similarity transformation? Which terms?
All of them except for the x, because you just do an x flip, right? And then, okay, no, because you accept and reject. So yeah, it's some combination of all of them, yeah.
I see. I ask because the last term is basically, I know it is a double commutator of ZZ and X, and I'm just curious if it has
This just comes from the Metropolis Hastings acceptance. This is exactly this question of this comes from, I need to know whether the energy went down or up, right? And so that I only know that if I know what the value of the spin of my neighbors is. And now you see that, well, these three terms, they don't commute. So there's a 2D phase diagram for this ground state phase diagram for this model. And I can draw it as a function of J2 over H and J1 over H. So if J2 is 0, well, then we know the model, right? I mean, then this is transverse field Ising model, right? If J2 is 0. So on this line from 0 to 1 here, I get, of course, a paramagnet, and then when J1 over H is 1, I go to the ferromagnet, right? But the full phase diagram, you should maybe trust me, is that basically there's this triangle here, which is the paramagnet. there's two ferromagnets, and then there's something which we call a cluster state phase, because if you take J2 to infinity, actually that's the parent, this piece is the parent Hamiltonian for the 1D cluster state. So, and you have a transition from there into this phase. Now, as I said, the H, the J, and the J2, they are all beta dependent. So there's only one parameter, right? There's a one parameter family of Hamiltonians that lives inside this phase diagram, which is this red line. And this red line goes from beta infinity at the origin, which is just sigma x, right? Because the ground state of sigma x is the equal superposition of all states. That's the infinite temperature state. And then it goes, when beta goes to infinity, it goes to this point over here at like 2, 1. And so it's at this tricritical point when beta goes to infinity. And so now this is essentially the whole story, is that basically, of course, in this 1D chain, the chain is always mixing, right? The classical chain, we know that, right? But at low temperature, you should get diffusion, right? I mean, domain walls in this easing chain, they're the hardest to get rid of at 0 temperature, but they diffuse, right? Because they just do a random walk. Actually, this diffusion comes from the fact that this tricritical point has Z is 2. But actually, all the other ones have Z is 1. So now this is the strategy, is that basically if you deviate from this line, actually instead of getting diffusion, you get ballistic transport, so you can prepare this state quantum mechanically faster than you could actually prepare it with this Markov chain, because the Markov chain has to be on this red line. But if you move away from it, it's not a Markov chain anymore. Because you can't, the similarity transform back doesn't actually give you a positive matrix. And so then you can do that faster.
Just to understand what you said. So if I solve imaginary time Schrodinger equation and do Markov simulation, I get exact same complexity, right? Because I have exact same gap.
Yeah, as long as you are on this red line, exactly.
Yeah.
Yeah, exactly. But then the point is that when you deviate away from it, you don't. And so this is the trick, right? So you can do adiabatic state preparation by moving away from this red line. And, you know, this red line for those, I mean, this is like a Roxar-Kivelson line, you know. It's like if you come from that, you could view it like that, you know. I have a Hamiltonian here that I gave you. If I didn't tell you how I constructed this Hamiltonian, you could be clever and say like, oh, there's a special line in this phase diagram, which is a Roxar-Kivelson point or line in this case, where I can solve the problem because actually it's secretly a Markov chain. And does this work? Yeah, so I mean, this is the same phase diagram, and now you can take different trajectories through this phase diagram. And you see that if you follow the red line, you get n squared scaling to reach a certain overlap with the final target. But if you, for example, take any of the lines that cross into the ferromagnet before, you get n scaling, so this is Z is 1. And if you actually come close to this cluster state, you get worse scale, you know, actually there, because this phase transition is kind of funny. And so this is like some way, you know, you could try to get speed up in general. So we've been sort of, yeah.
Is it possible to modify? Yeah, you can shut me down any point. So yeah, is it possible to modify like classical annealing path, not only changing beta, but something else to be quantum? Because during annealing protocol, you can say not just, I don't know, change beta, but also change some parameter in the classical, whatever. You know.
Yeah, you can do that too, right? Yeah. And I don't know, maybe if you're very clever, you could get non-diffusive scaling, but it's hard to imagine that, for me at least, you know, in this case, that you wouldn't get diffusion in the classical case, right? No matter essentially what you do. So, I mean, in the end, it's just, yeah, I mean, that's it, right? And I mean, I got inspired by Antonello's talk a couple of weeks ago, you know, on this, that I was like, we should maybe revisit this, because I think we can do this construction in general for many models, but actually in high dimensions, let's say for 3D Ising, we kind of gave up on doing the quantum Monte Carlo. We tried very hard to actually nail this phase diagram with quantum Monte Carlo, but it has like severe sign problems. But now I got inspired that actually maybe we should just do mean field theory on the whole thing. Anyway, okay. Yeah. What do you mean in terms of what? There is a phase transition. So there is a gap closing. At most points, the gap closes like 1 over the system size. But actually, not everywhere. There are actually funny points where basically the gap is exactly 0. So the phase transition is kind of strange. Yeah, exactly. And it has to do exactly with that. Exactly. So there's like an SPT. And yeah, I mean, it's in the paper. Actually, the point is that I didn't want to spend time on it, but basically now that I'm talking about it, you see that actually this is free fermionizable, right? I mean, so this is why we can solve this for such big systems, because if I do Jordan-Wigner on this X between the Z's actually just makes next nearest neighbor hopping on the fermions. And so you could solve this, it's just free fermions. But it's because this competition between nearest neighbor hopping coming from the normal J and this next nearest neighbor hopping, there are actually funny points where they exactly cancel. And because there's no level repulsion, you just get exact zeros.
So here, what is again, the protocol you begin?
Yeah, it's just adiabatic state preparation.
Yeah, so you start in the ground state of
you start just
beta
in the X polarized state, and you just do quantum annealing by switching off the transverse field.
and then it brings you to the
And then it brings you to the ground state of this Hamiltonian.
of the classical Hamiltonian.
Exactly. If you do this trajectory that starts here and ends in this point, then you get to the ground state of this quantum Hamiltonian. And by my construction, if you measure this ground state in the computational basis, you will get samples out of the classical Gibbs state.
But since beta goes to infinity, this is the same beta which you had previously, so it will correspond to
zero
the
temperature
Gibbs distribution, 0 temperature, which is just
here it's trivial.
wait, 0 temperature. Yes, so just the ground state. So it's not really the Gibbs distribution, but you can stop before.
You can start with some close temperature. Exactly. I mean, I'm just saying this because we can't solve this complicated model. So I just want to show.
So you don't have to go all the way to beta to infinity. You can stop a little bit.
Yeah, you can stop before and exactly. And then still you would get diffusion there classically, and here you would get ballistic transport, so it's faster. But of course, this is totally uninteresting, right? Because it's just the difference between L and L squared. It's just that this is a simple example that I can explain. But in the paper, there are we cook up some examples which actually come from this independent set sampling, where we have some graphs where we can show that the classical thing is exponentially bad. And we can get exponential speed up for these graphs because of kind of a level repulsion in the quantum case. Okay, yeah, I'm going extremely slow. That's what happens if you make new slides. So another example, which maybe I should skip, but it's basically this sampling from independent sets. So this is what you were asking, is sampling hard? Yes, actually sampling independent sets is hard. I can do the same construction. Again, there is some like Roxar-Kivelson line in a 2D phase diagram. This is, again, just a 1D chain, again, because then we can solve it. Not because it's particularly interesting, but this has like different phases. So there's a Z2 ordered and a Z3 ordered phase. And the funny thing is, again, just like in the previous example, actually your Markov chain is somewhat like fine-tuned in the quantum sense, that it really goes in this sliver between the Z2 and the Z3 ordered phase. And because of that, it becomes extremely slow because it's close to these two critical points. It's really squeezed in between. And again, yeah, if you basically go into the ordered phase, because the Z2 ordered phase is, of course, the maximum independent set, right? It's like, it's an independent set, and you cannot add another like black without touching another black, right? So if you go in that phase before you get close to the Z3 phase, you get another speed up, And I hope you get the point by now, right? That you can do this sort of more generally. And maybe one thing that is important that I want to show you, because it sort of will come back in a second, is that, okay, now you can think like, okay, that's all good, but like, how do we have any guarantee that this works, in general, or what can we expect? So it's good to always, I think, try this example of what I call marked item sampling. It's basically Grover's problem, but in a sampling setup. imagine that I create this dumb Hamiltonian, which has like all the states have zero energy, and there's just a projector to some randomly chosen bit string that has energy -1. I could do that, right? Of course, that's like if I now try to sample from the Gibbs distribution, well, okay, at high temperature, I will basically entropically be just sampling these guys. But then there's a first order phase transition by which I will basically always get this marked item state, right? So this is the canonical way to get a first order transition. And you can, again, follow my logic, construct this parent Hamiltonian. Again, it's embedded in a 2D phase diagram in this case. And okay, it looks maybe not so nice by now, but let me focus on what really matters. Again, this Roxar-Kivelson line is this red line over here. And it basically turns out that when you go to infinite beta, so low temperature, it has a gap closing, which is 1/n. Which is what indeed you would where n is the number of items, like the size of Hilbert space. And of course, because you have a random thing that you're trying to sample, you could just prove that it's not possible to sample this thing any faster than 1 over the number of items, right? But in the quantum case, actually what you get is that actually no matter which trajectory you take, as long as it deviates enough from the red line, you will always get level repulsion, and the 1/n becomes 1/√n. And it's really because this red line is approaching this infinite temperature result by really switching off the interaction between the ground state and the excited states. So it's really creating absence of level repulsion. So as long as you have any other generic point, you will get this square root speed up. So this is maybe some way to argue that actually this procedure from this perspective is sort of pretty robust, because it doesn't actually exactly matter what I do. It's that all of these classical Markov chains are fine-tuned, and they all have this sort of vanishing level repulsion in the end. So maybe one can argue that actually by deviating away enough, this gives you like a reasonable speed up. I see
If
it
I
all.
remember correctly, if you follow red line, but you slow down close to b equals to infinity, you can also get same scaling, no?
No, this is theoretically impossible. That's why this example is nice. Like there's no way to get better than 1/n. It's classically, right? Exactly. Exactly. There's nothing you can do. It's true that actually the thing that I may be cheating you on is that in order to get the quantum speed up of 1/√n, I need to slow down, right? So for the quantum case, I need to actually slow down, because if I don't slow down when I'm near this 1/√n, then actually you see that if you do normal Landau-Zener, actually the scaling is 1 over the gap squared, right? So to get 1 over the gap, I need to slow down when I get close to the gap, right? And so there is a somewhat thing that if you don't do your adiabatic state preparation well, you actually don't get the speed up, right? So this was a semi-intro and a semi-way of me trying to excite people to think about this problem, because you get very rich phase diagrams for these models. They give you sort of these kinetically constrained models that naturally come from this, and they all have interesting phase diagrams. So I just think it's kind of an interesting way to generate sort of funny phases of matter, maybe. Okay, so now, but you can also see that maybe it's not a super practical way for me to try to get speed up on a quantum device, right? Maybe it is, but it's not easy. So we were thinking a lot, can we basically improve this? And then it turns out that people at kind of IBM came up with a similar idea as us, and they even were good enough to basically publish this in Nature. So let's see what this idea is, right? So the idea, this is much simpler than what I did before, is to go back. Instead of trying to Gibbs sample from this state, so that is to prepare one coherent state, right, and try to get a sample by just using Born rule, I'm going to go back to my Metropolis Hastings algorithm. I'm going to go back to MCMC. And I'm going to just ask, but why don't I try to come up with some sequential procedure to use a quantum computer? And the sequential procedure could, for example, be that instead of proposing sort of single spin flips, maybe I should use my quantum computer to come up with interesting proposals. Right? Instead of doing single spin flip proposals, maybe I could do the following. I say, oh, I have a state Y. I'm now going to do some channel on it, which say is unitary. And I do a measurement X, and I'm going to say, oh, the new state X that I get out, this I'm going to check, does it have lower energy, yes or no? And then I'm going to do Metropolis Hastings on that, right? And why would you believe that this could give you possibly any speed up? Well, because you can make this unitary know about the Hamiltonian, right? So just like before, I just tried to convince you that, oh, kind of this quantum dynamics can be faster than classical dynamics because, okay, in this one case, it's ballistic instead of diffusive. So if you can make this unitary know about the Hamiltonian, well, then maybe it's a way to generate interesting many-body proposals instead of doing single spin flips.
Sorry,
So
sorry,
that,
this look, I mean, morally a little bit similar, at least in spirit, with what Tom was discussing yesterday a little bit, like
yeah,
in which you do a measurement and then you do an update based on how far.
but
So
exactly. But here you see that the only part where you use the quantum computer is to say that it's an input to a quantum channel, and then I
Okay.
generate an output, and all the rest is classical. Right?
Okay.
We can make the rest quantum too, but then we go basically back to the thing I've been discussing for
Okay.
15 minutes or
Okay.
more. So okay, they do this. Okay, what could you try to do? Well, it could be interesting if you take as the quantum Hamiltonian the classical one plus some small mixing term, you know. And now you can ask, maybe this quantum mixing term is going to be better than the classical mixing term, you know. And maybe I get more interesting proposals. And I want to ask, okay, is this true or is this not true? You know, that's going to be the remainder of the talk. And so just to show, in this IBM paper, they kind of apply this to the Edwards-Anderson model. So basically, it's just easing with random J's on the bonds on a 2D lattice in this case. I mean, lattice, it's N10 spin, so it's not really a lattice. Most of the examples are a 1D chain, right? Because, you know, IBM is this heavy hex architecture. So basically there's like 12 spins on a loop. So actually, yeah, I mean, it's like a tree, right? But anyway, let's say it's the Edwards-Anderson model in 2D.
Which is ground state is P.
Yeah, exactly. Which is still even then, that's still easy to do. Exactly. You should even go to 3D. Yeah, exactly. So, okay, what is that? What do they do? This is temperature. This is, again, this spectral gap that I was saying. And now you can have like a local algorithm, you know, classical spin flips. It doesn't work very well because it's not the best way to actually do this. And then here's the gap of the quantum results. So actually, you see that in this whole low temperature regime, which is the thing you want to do, this gap is like much, much bigger, you know, by orders of magnitude than the classical one. And you see they check the scaling here. You have, okay, maybe if you do uniform random guessing, then okay, the scaling is just like 1 over the dimension of Hilbert space, right? So then you can define this K here, which says how far you are away from that. And you see, as they argue here, that basically this K is pretty small. It's like 1/4, so you get basically exponentially better than local moves and uniform moves. But still exponentially bad, right? I mean, the scaling is still bad, but the exponent is like much smaller. So I think, we had similar result, I think, unpublished from way before that, and we never really knew what to do with it, but I guess this paper incited me to kind of think about the problem again. So, okay, how am I going to think about the problem? Let's see how much time do I have? Okay, well, let's see, maybe we can skip a couple of things. So one way, calculating this gap is very hard, right? As you can all imagine. So there is a neat trick, which maybe I can sort of explain. It's called bottleneck analysis, and it's a way to basically put bounds on the gap of a Markov chain, or in graph theory, it's basically a way to bound basically the spectral gap of graphs, weighted graphs. And so what do you basically do? You calculate this quantity, which you can call the flux phi, and it's the following thing. take your Markov matrix P, right, and ask in equilibrium, so pi is the equilibrium distribution of P, right, in this case the Gibbs state, right, it's the eigenvalue 1, equilibrium Gibbs state, and ask, apply P to pi, right, this tells you how much current, like how much did I move, you know, my distribution. But you see that I only sum over x's which belong to a set A, let's say, and then I have the complement of A. So I'm basically asking how much weight moves from A to its complement in equilibrium, right? That's what this formula says. Now I can, okay, let's define the following thing, that is, now try to find the set A for which this flow phi is minimized. That's why it's called a bottleneck. That's basically partition your graph in such a way that you minimize how much current flows from A to its complement if the whole thing is in a Gibbs distribution.
You ask that, let's say, A is half dimensional of the graph or no?
Yeah, well, in principle, you don't need to do it, but so if you don't put this constraint, the thing I will show in a second looks slightly more ugly. But so you don't need to do that, but if you put this constraint, then the following thing applies, that you can prove that the gap is upper bounded by 2 times this flow and is lower bounded by this number squared over 2. And this is called Cheeger bound. I mean, for reference, for example, the upper bound, everybody here, I think, can derive. The upper bound you can derive in the following way. This Markov chain, I could do this similarity transform from the first part of my talk, right? Then I have a Hamiltonian. Then we all know Rayleigh-Ritz, right? So this actually is just a way to express a variational wave function that is orthogonal to the Gibbs state, right? So the upper bound is variational in the usual Rayleigh-Ritz thing. You know, I can upper bound the gap of anything by saying, if I know the ground state, which we do because it's the Gibbs state, as long as I prepare a wave function orthogonal to it, yeah, I know that I can bound the gap, right? That's what the upper bound is. The lower bound actually is much harder to derive. And the lower bound is really tricky. But you see, I'm stressing it because you see that the upper bound, it means that if I don't do the minimum, if I have a worse thing, you know, yeah, then my upper bound is just worse, you know. And since we can basically, it's very hard to find the worst set, which if you want to lower bound it is really what you need. You know, if you want to prove this mixes fast, then you need to make sure that this is lower bounded. But I'm going to show you the opposite, right? Is that I want to show that I can prove that in some cases things mix slowly. So then it's okay if I don't actually have the optimal set, right? If I can prove that there is a set for which the flux is small, then I know the gap is basically smaller, right?
This holds for any graph, basically.
Yes. Yeah, I mean, I think so, yeah. And you see that you can immediately, if the chain is reducible, for example, then yeah, there is just one where it's 0, right? Because, so yeah, I think it does. There might be some caveats, but I don't think there's anything crazy. Okay, so let's get back to my example from before, because this is the one that's like Grover-like, you know, where basically I have no structure whatsoever. So I'm going to, again, get rid of all the structure in the problem and say, can I use the same trick, you know, like now with this MCMC to get Grover speed up, right? That is to use my quantum computer in this fashion to do it. And that's the paper we wrote with Aleph. And okay, the answer is no, basically. So we can prove using this bottleneck analysis, in which basically we say that use as a bottleneck just the flow between the ground state and all the other states, right? Because that's a natural way to partition this graph into 2 subgraphs, right? And we can basically prove that if you do that, we can calculate this flux in the Gibbs state. If we calculate this flux in the Gibbs state, we can just prove that this flux is basically exponentially small. You see 1/2 to the n. And then there are some factors here, which if beta is big, all become small, right? And Q, you see here, Q, I still left it arbitrary. So the nice thing about this proof is just that this holds for any Q that you can put in. So actually, it's not a statement about, so this also answers Anatoly's question that can I cheat and come up with a better classical process? No, actually, this is true for any Q. So it's actually true for any unital quantum channel because all unital channels can be written in this form. So we can just prove that you cannot do Grover with this. So this is much less powerful than the previous Gibbs state construction, essentially because there's no coherence between different layers. Right? And killing this coherence does kill a lot of the quantum advantage. Okay, so is this it? Should we give up? Maybe we should give up, but now we can look at the same examples again. You know, I can take the Ising chain, and now you see that in my quantum proposal, maybe I didn't stress it in the beginning enough, but there's like some parameters, right? Which is basically how strong is this mixing term and how long am I waiting for, you know? Like I'm quenching and then I'm waiting for the system to thermalize, let's say, but how long do I wait? And so I can look at the gap, let's say numerically for an Ising chain of only 8 spins, you know, then I can do this. And you see, this is the gap as a function of the transverse field and time, you know, and it looks like, oh, there's some pockets here, you know, some interference fringes where I could do very well. So this is like we want to find, you know, where this can do very well, right?
So, but in each step, you can change your Hamiltonian, right?
Yeah.
And then you can realize quantum annealing, or no? Because suppose you change whatever this mixing term slowly and becomes say bigger and bigger.
But you still measure, right? The point is that you measure, right?
But
so
you just, because time, I see.
Yeah, exactly.
You cannot make time.
No, yeah, exactly. So of course, you could say if you do arbitrary weak measurements, maybe, yeah. But you see, this is like I do projective measurements, and and I'll get to that. I'll try to sort of start wrapping up, right? So, okay, long story short, again, this is like some analysis similar to what would be done for this IBM type paper, trying to look at when the gap is big. And you see for small systems, there are these like super kind of nice, maybe cool interference fringes where this could work very well. But again, we can do this Cheeger bound, you know, on the Ising chain now exactly the same way. We construct a set, we do the partitioning. Lo and behold, if I go from n to 8 to n is 100, actually the gap, you know, becomes 10 to the minus 5. It's basically super bad in this entire regime, and it's only good at extremely small transverse field. And again, the formulas, if you like them, they don't matter, but we can basically bound the gap again from above by this procedure, and you see that there's like 2 factors in here. One, some prefactor, 1 over n, and then you see here again, there is some exponentially small thing. And this is, I mean, for those who have looked at like dynamical phase transition in the Ising model, these formulas should look familiar because they're the same things that appear here. This is basically bounded by some Loschmidt echo. That's the point. And this is always exponentially small, right? Unless this lambda over here itself is 1 over n, right? Because just basically overlaps between wave functions are exponentially small. And so you can just show that this is only 1 over n when the transverse field is perturbatively weak. But then essentially you're just going back to the single spin flip thing because you make your transverse field so small that actually you can do perturbation theory in the number of flips. But yeah, then of course there is no quantum advantage because you're just getting back that actually it's actually terrible unless you do the perturbative thing.
H needs to be 1 over square root.
Yeah, exactly. Basically, h is 1 over square root of n. And then you basically just get back the normal classical scaling. Okay, and then in light of time, you see the thing that is related to thermalization is that now we can try to understand what's going on. So in general, I would say as long as I do a quench for my proposal can just be expanded in eigenstates like this. And as long as there's nothing funny happening about like scars or some like degeneracies in the spectrum over here, I should be able, since I don't really know when I'm supposed to measure anyway, it should be robust. So maybe I should time average this. But if I time average this, then you see that this proposal basically factorizes in some process, which is that go from a classical state to an eigenstate n, go from that eigenstate back to a new classical state. That's how you propose, right? And using the same trick, we can basically therefore upper bound. We can write this bottleneck again, you know, and this bottleneck now just becomes, it's easier to see in sort of maybe like that. This bottleneck just becomes the overlap between these two distributions in energy eigenspace, right? It becomes, you can view this as go backwards from x to n and go forward from y to n, right? And then you need to compute the overlap between these two distributions. And so the whole game would be that if you want to make this bottleneck, which is the gap for the Markov chain, non-exponentially small, then you need to make the overlap between these eigenstate distributions non-exponentially small. But now you see how this is very difficult if you have a many-body problem, right? Because okay, so this is pictorial, right? This is, imagine I separate them by energy, then I go from the classical energy to the quantum states, and from this like subset, you know, the other set, the complement of this set, to the energy eigenstates, and I want to maximize the overlap between the dark blue and the light blue, you know. But this is very hard. And I mean, how hard is it? For example, you can do just stupid Cauchy-Schwarz on this previous expression. And if I do that, then basically this shows immediately that this gap is basically bounded from above by the purity of these two distributions, right? By the geometric mean of the purity of these two things. But that in and of itself, of course, is limited by the IPR of the eigenstates. But now you see that if you don't want this to be exponentially small, then the IPR of the eigenstates in the classical, well, of the classical states in the eigenstate basis cannot be exponentially small. So you kind of need to be Fock space localized. But if I'm Fock space localized, what's the probability that I'm going to move high energy states to low energy states if I'm Fock space localized? Yeah, that's exponentially small too. So you see that you get this big competition between, and this is why I wanted to give this talk, between like ergodicity in the quantum sense and entropy production for this classical process. Because the point is just that if you have a thing that mixes very well quantum mechanically, actually by this quench procedure, you're necessarily producing a lot of entropy, and this basically makes the mixing bad, right? Unless you can create a funny scenario where basically the IPRs are sort of not as big as they maybe are generically. And so maybe you want some like multifractality or something like that, right? And so I'll skip the rest. You see, we checked this, that indeed these are the IPRs as a function of energy. Well, the labels are missing. And indeed, we can check that at these optimal parameters, the low energy IPRs sort of have different scaling from maximum. And that's exactly where you get the most speed up. So I think now the quest is sort of on, in the sense of like, can you get quantum speed up for this sampling by somehow generating multifractal or somehow weakly ergodic sort of states? Because if you're too chaotic, yeah, then it's like a problem. Like you clearly, I just proven to you that it cannot actually be any better than exponentially bad. But maybe there's somewhere in between. And so maybe the best speed up is to do something quantum about phases that aren't too chaotic, but aren't localized either, right? And so with that, I'll skip this thing. I'll come to my conclusion is that basically sampling is some way we can try to get quantum advantage, but maybe we want to do it for interesting problems. You could do Gibbs sampling. That was the first thing I talked about. There we have some good results in the sense that, yeah, clearly we can show there can be Grover type speedup. So there's some interesting, I think, way to go to understand for more interesting models what are the phases of matter that we get from this like construction of these parent Hamiltonians. And then for this Markov chain Monte Carlo, yeah, I think it's an enticing idea because it could be, you do a lot of post-selection. So because you see you have this Markov chain running anyway. So if you would have noise in your machine, yeah, you automatically sort of kill this noise anyway, right? So that's great. But at the same time, I think I maybe convinced you that it has like much lower power. But there is still some hope for speed up, I think. except you need some structure, to exploit. And so that's, I mean, the other way to say is that in this previous case where you have this huge degeneracy, you cannot actually get sort of multifractal states because you have this big degeneracy. And so, I mean, finally, just to say that in the end, you see this type of arguments about tunneling between different minima using this quantum computer are basically not the way to think about it. The way to think about it is think in terms of this like mixing between eigenstates. And that's it.
Thank you. We had already tons of questions, but let's see if there are more. Yes, there are.
Suppose you have an algorithm a classical algorithm which doesn't have detailed balance but can find a solution. Like for example, there are
Yeah.
which I don't know, like belief propagation, this kind of things. Which can you nonetheless use this kind of quantum thing to speed up?
We have been thinking about it. We currently haven't found a way to do it. And the hard part is basically that if you don't have it and you want to guarantee some kind of Gibbs state, then your acceptance and rejection depends now on the proposal probability, and then it becomes kind of hard.
Why does it have to be a Gibbs state? Why can't it not be like some function of, I mean, not an exponential, it can be something else, right?
Yeah, I think
as far as
the game is on. Yeah, if you're happy to do something like approximately find some low energy state, like maybe in cavity sort of method, then I think things are fully open. I don't have any interesting thing to say about that. I can tell you the thing we're doing now, which I hope will be out maybe in a couple of weeks/months, is that basically you can still generate detailed balance, like symmetric proposals, and thereby do detailed balance by having a Hamiltonian protocol that's symmetric in time, right? So that has time reversal symmetry and is symmetric in time. So then you can do the thing. You see, part of the problem can be fixed if I can avoid that I, by quenching, introduce huge occupations, a big window in energy, right? So I need to go to a big enough transverse field to make the eigenstates delocalized, right? Because if they're localized in Fock space, then nothing happens. But if I put a big enough transverse field, then every time I quench, I pump a lot of energy in the problem. So now the thing that I hope we will have out soon is that actually if you adiabatically switch on and off the field, then you can avoid, by just going slow enough, that you pump energy in the system, right? And then you can tune the energy window independently from the mixing, right? Because the ergodic quantum mixing is set by the final value that I go to and how long I will wait for the system to thermalize there. But the energy I pump in the system, I can control by going just slower. And so by that, we can actually get like much bigger advantage.
More questions? Okay, if not, let's thank Dries again.
Okay.